Hello. So this time I wanted to do something different. At work we had this discussion over type classes and especially a type class that is defined in Play framework. And well, this colleague, he wanted to see if it would be possible to derive these type classes. And since the work that I did on Helenus and how we are using Shapeless to derive type classes for row mappers or utility codecs and things like that, I thought it would be a good idea to give an introduction or kind of like show some examples of how I approach doing these implementations. I by no means no expert on this. I just happen to have some experience with the library. So there are two ways that, or two libraries that we can use to derive type classes, and one of them is Shapeless and the other one is Magnolia. I only have experience working with Shapeless, so this session will be using this one. So Shapeless is a library that allows us to do generic programming in Scala. It can be used for way more than Typeclass Derivation, but I would say maybe one of its most known use cases is Typeclass Derivation. So basically, what generic programming means is that we can deconstruct types, complex types such as case classes or tuples by its part or in its part, and then do some processing, ignoring the particularities of that specific type. That this will become apparent when we go over the examples. So first of all, what I would say is that it's important to know what a type class is. So a type class is a pattern that let us use or define some ad hoc polymorphism. And as the essential Scala book says, type class is a trait with at least one type variable. The type variables specify the concrete types the type class instances are defined for. Methods in the trait are usually use this type variable. In this case, what we have is in this example, we have this trait example type class with a type variable a, and then for that we have a method do something that takes a as its input parameter. This input parameter, this a, could be also on return position, but yeah, this is just an example of how to do it. Here are, let's say, maybe some other example where we have an HTML writer, and we can see how some type parameter a gets parsed into or transformed into some HTML, and in a form of a string. Now, usually a type class has three components, and two of them are mentioned here. So on the one hand, we have the trait. So this defines what operations the type class defines. Then we have the instances. So we need to create instances for each one of the concrete types that we're going to use that type class for. So in this case, this HTML writer, we see an example here for person. So this is an instance for person, and we have to either create them manually, or as we'll see, we can use Shapeless to derive these instances. And this is what Typeclass derivation means, not necessarily deriving the whole type class. So that's on our responsibility, or maybe on the responsibility of the library designer, because maybe the library designer defines a type class, and then users have to implement instances of that type class so it can interact with the library, as we'll see in the examples. And finally, the last component of the type class pattern is points where you can plug those type classes. First of all, we're going to see we're going to mention this book. So this book is also available on at _IO. So this is the book that I read to understand how to do typeclass derivation. At the end or the later sections cover more than typeclass derivation, but most of the book is focused on that. It's a very nice book, easy to follow. I would definitely recommend it if you want to delve a bit further. In this case, well, it goes and it will explain in way more details than I will for this use case. But just to explain a bit or show a bit what generic programming means is that, for example, we have two case classes, employee and ice cream, and you can see that both of them have 3 fields, and both have the same types in the same order. So in this case, we have name, that's a string, number, that's an int, and then manager, that's a boolean. And for ice cream, we'll have name as a string, number of cherries as an int, and in cone as a boolean. So what generic programming allows us to do is to forego these types, to forego the fact that we're dealing with an employee or an ice cream, and just consider the parts that we are defining here. In this case, what we can do is let's copy this and let's go to the console. So I already set it up. So let's see. So let's create one of this, and also let's define ice cream. So what Shapeless allows us to do is treat them in the same manner, and for that it introduces different abstractions. One of the abstractions is generic, and this generic abstraction lets us convert from the case class, so from, let's say, the complex type into its constituent parts. So let's go ahead and let's import Shapeless. Let's import everything. And then from here, what we can do is we can use this abstraction that lets us go back and forth. That's called generic. So let's go gen employee, and let's instantiate. And now we have the representation. So the generic representation that we can see that here we have a type-dependent type, a path-dependent type, sorry, that is string, int, and boolean, and finally HLists that I'll mention that in a moment. So what we can do is we can also define one for ice cream. Now, if you notice, the types are the same. So int as string, int, boolean, and HLists. Now, what we can do is we can do this conversion from this case class instance. So let's call this Bob. And let's call manager false. So once we have this, what we can do is we can convert Bob into its generic representation using let's call gen Bob, and using the generic employee. We can do it, I think it was, let's get these methods wrong. Yeah, it's not. From is to. Oh, sorry. Might be. Yes, to. So once I have done this, I have converted this into the representation that we have for Bob. And another thing that I could do, I could go the other way around. So I could either use gen employee to go from genbob, and I get the employee back, or I could even go and treat this as ice cream. And since the fields are the same, the types are the same and are defined in the same order, this doesn't complain, and yeah, we can get an ice cream from Bob, if that makes sense. So let's take a look at genbob. So generic Bob, this is a representation, and actually what we can do from this path dependent type is that this represents an instance of what Shapeless defines as an HList, or as an heterogeneous list. So as we know, whenever we are doing whenever we are working with regular lists, so let's say L, and we do 1, 2, 3, this list is homogeneous, so there is only one type parameter for every element in the collection. If I by some chance try to introduce different types inside the collection, what happens is that the type parameter is completely different, so it's no longer an int. It has to be represented by the common ancestor between all the types contained in that collection. Now what happens is that what I could do is I can define the HList type, so I can define the type for each one of those components with Shapeless. So in this case we have a string, and then we have an int, and then we have a boolean, and finally we have an HNil. So I could do genbob, and then that works. So because I have defined this as a type, so this is why it's mentioned this is heterogeneous. So each element in the list, it's accounted for. Now, how do we work from here? So why is it important that we can convert these case classes into some generic representation? So the reason is that once we have deconstruct them, what we can do is we can think about in recursive terms on how to approach this typeclass derivation. And this is an example. This is something that will go again and again during this session. So maybe it's not clear enough, but I'll mention it during the examples. So okay, let's start with the example. So let's start with something simple. So Scala defines this trait, or well, in this case, this type class called ordering. So ordering is a trait that we can implement, and the thing that we have to implement is we have to implement a compare method that takes two values from the type parameter that is used to find, and then what we have to do is we have to return an int. This works as like a comparable or comparator, something like that. So it's kind of like we're comparing two types, and we're according to the rules, if the result is positive, that means that in this case, let's take this. So x and y. If the result is positive, then x is greater than y. If it's negative, then it's less, and then if it's 0, it's the same. We can think about ordering in the same way as we are thinking about integer subtraction. So if I have 10 minus 6, I'll get 4, and by being positive, that means that x, so the original number, the number in front, is bigger than the number than the other number. So what we can do is let's import that. So this would be Scala, math, ordering, and then what we can do is we can invoke we can summon we can summon the different implementations. So let's say implicitly and ordering of int, right? And what we can do is we can say compare, and we have 10 and 6. And since 10 is greater than 6, then we get 1. If we do it with 10, same value, so we get 0. And if we swap those things, we get -1, right? Because 6 is less than 10. Now we can also invoke the same. So for string, let's say that's another type, and we could say var and foo. So from this we get that the result is -4. The reasoning is that it compares what's the position in the alphabet, and yeah, compares it's in a let's say element by element. So let's say I could say bus, and yeah, we get the same, right? Like we compare element by element in the string, and position by position, and then we come up with a value. Now, in a sense, what we are doing here is we have two of the components, right, of the type class. So the trait we have already defined. The instances are here, are summoned with implicitly. And the way that this is used is that, for example, in sorting.quicksort, so this is a method that expects an implicit ordering, and we can see that ordering. Yeah. So no, sorry, I want to go for sorting. Yeah. So where is it? Implicit. Yeah. So here it's calling some implicit of. Okay. Yeah. Here. Oh yeah. It's as a type bound. So in this case, we are requiring this to be implicit. Okay. So. The first thing that will give a try is how can we create instances for ordering type classes. So sorry, instances for ordering case classes. So if I try to summon the ordering for an employee, what I will get is that there is no implicit ordering for employees. So how could it, right? Like how could the Scala library come with an implicit definition, or an instance of a class that I create? So yeah, we let's go ahead and let's try to import this. Let's try to create an ordering for employee and for ice cream, right? The way that we're going to approach it is we're going to pick each one of its parts, and we're going to compare first the first element, then against the second element, and against the third element, and we're going to delegate how the comparison works. This is similar to how string comparison works, right? Like the first element would be compared against the first element, the second element against, and so on, and then we'll return the first one. So let's go ahead and let's do it on let's do it on this file. After this, we are going to show how to do it with the I'm going to show you how we did it for the example, or the thing that this colleague wanted to do with Blade Framework. So what I'm going to do is I'm going to define an object, and let's say let's call it generic ordering. Now, as I mentioned, the way to think about, since we are dealing with an HList is a list, and in functional programming we tend to think a lot about recursion. So we are going to work on recursion the same way, right? Like let's say that whenever we let's say myMap, we define a method called myMap that takes type parameter, and we have a list, a regular list, and what we do is, sorry, missing B. Then what we would do is, let's say that we want to implement our own version, we would do something like this. So we would have a list and then a method function that goes from A to B. So we do the map, and finally this would be a list of B's, right? And the way that a way that we could do it recursively is that we would do it. We would do, let's do match, and what we would do is if it's nil, so we just return nil. Otherwise, if it's a value, if it's a cons, what we do is we call the value with head, and then we concatenate with next, and then the function. And this is what we would do, right? Like we would define it recursively in this manner. So what we define is that a recursive operation has two cases. It has the base case. So this is the simplest solution for the problem. So the problem has reached its smallest problem size, and that's what we solve. We don't do any more iterations or any more recursions, and this would be the iterative case or the recursive case. So what we do is we think about typeclass derivation in the same manner. We are going to have a base case, and we are going to have an iterative case, and we are going to have one more step, and that's converting from our case class instance into our generic representation of an HList. So let's go ahead and let's start with that. Let's work through it. So let's clean this up and let's do the steps. So what we are going to do is we're going to have a base case, and then we are going to have an iterative case, and then we're going to have a conversion. So let's start with the conversion. Let's start with let's start with the conversion. So the conversion is going to be an implicit function that let's call it generic ordering, and this is going to use two types. It's going to have the original type, so the type that we are going to derive these type classes for, and in this case, let's say employee or ice cream, and then we are going to have some type variable for its representation, right? So the representation that we saw, let's see if we already have it. This representation, right? This is the type parameter that this represents. So obviously this the book goes in more detail, so I would encourage you to do that. So once we have this function, let's define the type, right? So the return type, and then let's talk about the parameters. So the return type is going to provide an ordering of A. And let's do something like this. Okay, so what we need here is we need two things. So on the one hand, we also need some we need to summon the generic representation just like we did in the console. So let's call it gen, and then let's call this generic. Oh, I didn't import. Let's import Shapeless. The generic representation of A, where R it's the representation. And another thing that we want is once we have this generic representation we can map from A to R. What we want to do is we also want the type class for that R. So this method is going to convert, and then it's going to delegate, once it has an R, it's going to delegate it to the instance for R. So what we're going to have is, this is also going to be implicit, and this is going to be, let's say, R or Deriving R, for a lack of a better name. Now, once we have this, we are ready to do the conversion. So let's create a new instance of ordering, and then what we are asked here is we are asked to compare. Sorry, let's put it like this. We are asked to compare A and A, but we don't know how to compare these two. So what we are going to do is we are going to actually convert those to R's and delegate to ordering R. So what we are going to do is we are going to use the generic, and then this would be 2. So we have an X, so we are converting X from A to R, and then we're going to do the same thing for Y. Once we have done that, we delegate to how this works. So now once we have done this, now we have to provide implementations for this ordering of R, which we'll do, as I mentioned, in a recursive fashion. But instead of having like only a single method, we are going to have 2 different methods for each case. So I always find it easier to understand what's the base case for this, and usually, or as I mentioned on the on my map, this is the last element of the of the position. Sorry, the last element in the case class. So what we can do is we can say we're also going to have it implicitly. So we are going to have an implicit method. Let's say generic, and let's call it HNil. And this is going to be an ordering of HNil. And so this is Life's case. Remember that we have, when you have a map, we have the nil, and then we have the cons. So in this case, we're going to consider the cons, and we are going to do this implementation. And here, it doesn't really matter. Like, let's say that HNil is just the last element in the position. So we're going to say that this is 0, right? Like these are 2 equals. Now, once I thought about that, I don't need anything else here. What I need to think is about the iterative case. So the iterative case is where I look at one element at a time, and if I do something with that, and then I continue with the rest of the list, with the rest of the HLists. So what we're going to do is we are going to define an implicit method as well, and let's call it generic HList. Now, this is going to have the element that we are going to consider at the head of the list. So this is a type parameter, and we are also going to have the tail that this needs to be needs to be an HList. So let's do it like this, and once I have done that, let's discuss about the parameters later. But then what we're going to do is we are going to define that this is an ordering of H, and let's say prepended to the type T of the tail, and that's how it's going to work basically. What will happen is that at some moment this R is an HList. This ordering is going to do some implicit search, and it's going to match against this. So in this case, let's say for the employee, that's a string, int, and Boolean. It's going to match first against this one, this is going to be a string, and then this is going to be an HList that contains the int, the boolean, and the HNIL. Once that's decomposed, we're going to have another method. We're going to call the compiler is going to try to find out the ordering for t, and it's going to call this method again until it reaches the end of, on the implicit search, the end where it hits the HNIL. So let's do ordering, and let's implement that. So what we're going to do is we are going to need some implicit values. So let's say ordering h. So we want to know how to order a string or an int or a boolean, and then we are going to also need an ordering of the tail, because we may need to delegate. So let's see if I can. I don't have a Scala FMT, so this is why it's looking so poor. Okay, so let's do this. So what we're going to do is we are going to define a variable. And sorry if I get this wrong, but this is the first time I'm trying to do the derivation for ordering. So what we're going to do is we have an ordering of h, and we are going to compare, and we need 2h. So what we're going to do is we're going to have x. So x is the first HList, and we're going to grab the first value. Then then we need the other value to compare it against, and we are going to do head. So once we do this, what we'll do is, if these values is different than 0, we're going to return that value, because we have already compared these two elements and they are different by a representation. But if they are the same, then we're going to compare it against the next one. So if comp it's not 0, then what we're going to do is we're going to call ordering t. So we're going to delegate to the tail, and we're going to compare x.tail against y.tail. Otherwise, we are going to just return the comparison, and that's it. Always about 0. Okay. Yeah. Oh, sorry. It's the other way around. No, it's like this. Yeah. So if it's the same, then we go and delegate it like this. So once we have done this, we should have enough to do the conversion. Okay, so I had to do a quick pause because I was having a bug and I couldn't understand where it was coming from. So yeah, the reason is that I had some parentheses here. I don't need that. Couldn't find it properly. Couldn't find a way to apply the function. So now once I have this, then should work out of the box. So what I did is I already imported Shapeless, and I also imported genetic ordering, and then what I should be able to do is I should be able to employee ordering of employee. I don't have it created, I think. Yes. Okay. So now employee ordering of employee, and then I should be able to call it implicitly ordering of employee. Yes, great. So that worked. Now what I can do is let's create Alice, and that would be Alice, and then let's say 42, and let's say that she is a manager, and then let's create Bob again. And Bob is not a manager employee. Now, what I can do is I can do this ordering, and I can compare Bob and Alice. Oh, bot. And that's what I get. So this compares first Alice, and then and Bob, the strings. If I do something like this, then I should get 0. Right, so I have derived. Maybe what I can do is, let's do Alice 2, and then let's do with 40, and then if I compare Alice with Alice 2, then I get 1, and that's because, well, Alice has 42, so that's bigger than 40, and that's why I'm getting this. So yeah, that's basically like how we would do it. So if we go back to the code, we first have a conversion. So we convert from this case class instance into the genetic representation by summoning that implicit. Then we also summon the implicit of the type class that we try to derive for that genetic representation, and then this goes, the compiler picks each one of the parts and each one of the types, and then says, okay, I want genetic ordering for an HList where its head is this type, and then the tail is some other type, and then it deconstructs one for one. So if we think about like how would the call stack look like for this, it would be, so we have a genetic ordering of employee, and the genetic representation would be string, int, boolean, and HNIL, right? So that's a representation, and then the compiler will try, so it will derive this, right, from this value, and then it will go and look for an ordering of this type, right? Now, what this will do is this will go and call a generic HList, where the head is a string and then the tail is this one. Now, the ordering for H, that's known. This is a string, so it's available implicitly. And then what it will do is it will say, okay, yeah, I need to find for this, I need to find an ordering, ordering of this tail, right? So then what it will do is it will again look for it. We know that the implicit generic HList provides an ordering of by looking only at the return type. It knows where to find it, and this will call it again. So this would be generic HList, where this is an int, and then the tail is boolean and HNIL. Then this would be the same, right? Like we would have an ordering of boolean, and then the tail would be an HNIL, just like, let's say, and then this would be, okay, one more time, this would be an HList of HLists, and then this would have to find again an ordering of HNIL, which it can get by calling generic HNIL, because that offers the type that the implicit search is looking for. So this would be basically the cascade, and how we can think about this recursive algorithm where we pick first the first element of the HNIL, of the HList. We do something with it, and then we delegate if we need to do something further. So okay, so that's basically it for ordering. Now the example, or the thing that this colleague wanted to do, they wanted to use this QueryStringBindable. So that's defined in Play framework. So what this does is, for a given query parameter, several query parameters, we can compose a more complex type. So in this case, we have an endpoint that accepts a from and a to as query parameters. But then if we go to the action itself, so how it's implemented, it doesn't have two parameters, from and to, of type int. What it has a parameter of type hRange. So hRange, if we see, this is coming from, this is a case class that the user has defined. And then what we have to do in order to let Play be able to convert from these simple types into this more complex type, is we have to introduce an implicit instance of QueryStringBindable of hRange. So if you see here, we have an implicit definition, implicit function that is using also some implicit for each one of the types, the elements that we have here. So you can see already how this is working, right? Like and how this is similar to what we were doing so far. The only difference with this QueryStringBindable and the type class that we have derived previously is that here we need to have access to the field names, right? Because we need to know how this from field maps to the from in the string, in the query string, and also the to. And we haven't been doing that with generic. So let's go ahead and let's take a look at that. And here we are going to think about the same steps, right? Like what I'm going to do is I'm going to have a base case, I'm going to have an iterative case, and I'm going to have a conversion. And then if you see here, I have derive QueryStringBindable that is extending query string. This is sort of like a way to, or can be used as a way to restrict where the compiler looks for implicits. I've seen some libraries, well, Helenus does it, also Circe does it. They have this separate type hierarchy that is used for derivation, for automatic or semi-automatic derivation. So let's create the instance method first. So what we want is we don't want to mark this as implicit. We want to actually do some semi-automatic derivation. That means that instead of having this thing implicitly that the compiler can look for, we'll have to implement this for, or we'll have to add it somewhere, like in the companion object or in the package object of the project, of some, let's say, API or whatever. So what we're going to do is, let's do apply, let's do the type parameter of the class that we want to make string bindable, and then here we're going to have an implicit, let's say DQSB, so derive QueryStringBindable of A. And here what we are going to do is we are not going to return a derive QueryStringBindable, we're just going to expose this type. And since, well, because of inheritance, yeah, this is, and finally we just return this value. Let's put it here, and that's it, right? Like now we can summon someone using this method that we'll see in a moment. Now, okay, so let's start with on the same way that we did before. So we are going to have an implicit function that is going to have a generic, let's say QSB for QueryStringBindable, and again this is going to have two type parameters: the type of the object that we want to derive this type class for, and its representation. Now, once I have done that, what I want here is I want to return derive string bindable of A, and now the compiler knows that by calling this, if it can prove or if it can find the implicit parameters that we're going to define just now, then it can construct derive QueryStringBindable for A. So what we're going to do is we are also going to require some implicit parameters, the same thing. So we need the generic representation, but this is going to be a bit different. We are not going to use generic like we did before. What we're going to do is we're going to use labeled generic. If you're wondering why are we using aux, although I didn't explain it, instead of doing it like we were doing before, like a generic and then just a type, it's better explaining the in the book, but it's based on a Scala 2 limitation on the compiler. Yeah, you can probably read that there. And finally, what we want is we want to have a QSB for that representation, right, like we did with the ordering. So what we're going to do is we're going to find a derived QueryStringBindable of R. Okay, so we have that. I never know if it's a line or not. Anyway, so once we have this, let's implement this, and here we have two methods to implement: bind and unbind. So if we go back to the example, what we see is that bind is trying to go use a key and a map of parameters, and is trying to construct an H range. So if we see the method, the signature, we can see that it takes those parameters, and you need to return an option of either a string that represents an error message or the type that we try to construct. So let's say in this case this will be going from a string to a case class instance. And then unbind does the opposite, so it takes a key and then an H range, and it returns a string. So it tries to decompose those into a string or a query string, in a query string form. So for this it would be quite simple, right? What we want to do is we have QSB, and what we have is we only know how to unbind for a value of R, not for a value of A. So as we did before, we are going to go from an A to an R. So this will be value. And then we have delegated it, and here what we're going to do is we're going to do exactly the same. So what we're going to do is we're going to have QSB, and then we're going to bind, and then we are going to say that this is a key and the params. And now I have to do the adaptation not when I call the method, but actually with the return type. So what we're going to do is we are going to map. Just let me get my notes. Map, and then we're going to do exhaustive. Let's deal first with the easy case. Sorry, with the right case. So what we are going to do is we are going to construct another right value, and what we want to do is we want to go the other way, right? We want to go from an R to an A. So we are going to do from, and then we are going to have the value that's of type R. And finally, if it's a left, that means that something went wrong, and we can just return the error. And that's basically it, right? Like we only perform the conversion here, and we delegate to the other method. So now once we do this, what we can do is we can construct the iterative case. So let's go and do that. So this is the same thing. We provide an implicit function, and let's call it HList QSB. Now this is going to have H, right? Just because we have the value in the head of the list. It's going to have a T that extends an HList, and then the return type for this would be derive string QueryBindable of something that I'll show in a moment. So and a thing that we need here to take into account is also the as I mentioned, the field names. So in this case, H range has from and to. That in Shapeless is also introduced as another type. This is something that again the book goes in detail. I'm just going to skim over it and just going to give you the definition. So the field has a type K, which derives from symbol. So from here, what we're going to do is this is going to return, instead of being an H and T, like we did with ordering, like we did here, what we're going to do is we are going to compose this K and H to construct a field type of of K and H. I put an extra. Yes. Okay. So once I have done this, I have created. I'm saying that this is an HList where the element is actually, let's say, a key value pair, if you will, or let's say a key being the field name, and H being the type of the value that represents. Now let's create an instance of that. Actually, let's new derive QueryStringBindable, and then we have the implementation. And here what we're going to need is a few things. On the one hand, what we need is we need implicit values. So we're going to need a way to convert the value of, let's say in this case, if we have H range, the int value. So let's do head QSB, and we here, instead of using a derive QueryStringBindable, let's just use QueryStringBindable, just because we want to deal only with simple types, let's say. So in this case would be of type H, so we are not dealing with the field name, we're only dealing with the field value type. Then we are going to have to use a witness. So a witness is something that we can get the field name from. So this is going to go from here, and what we're also going to need is a way to, let's say, if we already work with the head of the list, then we need to work with the tail of the list, just like we did for ordering. And here we are going to require derive QueryStringBindable. So let's this will be a type T. Now once we have done that, let's go ahead and let's implement this. So for the unbind, what we're going to do is we are going to do it quite simply like this. So we are going to grab that QueryStringBindable that knows how to convert an H to a string. We are going to call it with key, and we are going to have the value dot head, and that's it. So if we see here, we have a string, and we are going to concatenate that with calling the tail, combined, and then key, and then the value dot tail. So again, we grab the first part, we do some work, and then we delegate to the other implementation. Yes, yeah. So now one thing to mention is that here in this case, the implementation that I provided is wrong because it's using key. And if you see here, for from we have to use from, and for to we have to use to instead of key. So let's go back and let's use the field. So let's do private val and then query param name, and we're going to use the witness to get the value of k and then get the name. So right, yeah, right, this will be here. Yeah, it could be there as well. Doesn't really matter. So once we have this, I do it like that, and that's it. So here, when it's going using or let's say dealing with the first field with from, then this is going to have the value from, and it's going to unbind it there. Now let's go ahead and let's work with this. So what we're going to do is we're going to do the same thing. So we are going to go ahead and get head QSP that knows how to convert, knows how to do it with bind. So here we are going to look for the param name, and we are going to use the parameters that we were provided, and then we are going to flat map. I'll explain the reason why. So let's do exhaustive, and for this, let's say that here we have some error, right? And we have to return an option of an either. So let's do some left, and then let's say couldn't bind parameter, and then we just go and provide with the error. So now once we have this, we just hand it over. But then what we need to do here, what we have is we have a value of h. What we do need is we need to keep going. We need to start delegating so we can construct a more complex type. So what we're going to do is we are going to call QSP. We are going to bind with the key. Notice that here, whenever I'm binding, I'm ignoring it because of how range is the example is defined. But usually, what we would do is we would combine these two. I think that there's an example below that shows something more complex. Anyway, so we delegate there, and here we have a D. So what we are going to do is with this, here we are going to map here, and we are going to do exhaustive again. So if it's an error, let's just return that error. We don't need to specify it, so we don't need to do anything here. Let's say probably the method that deals with this already added this description. But now here, let's say that we have a head, and here we have a tail. Now what we need to do is we need to construct the type, and the way that we do that is, so we have to provide sum of right, and what we need to do is we need to construct first the field type, so this component, and then the list. So for the list, we already have it here, right? We have a T. What we need to do is we need to use the witness and the value, and then we can use the head. So this constructs the first element in the case class with its name, and then what we need to do is we need to concatenate it with the tail, and that creates this HList representation. Now this is complaining. If someone knows how to fix this, usually what I do is for some reason it cannot understand that this is type. What am I missing? Oh, right. Yeah, I don't need this. Yes, for some reason it cannot understand that it's this type, so of t. So yeah, I need to just do it like this. Actually, yeah, no. And once I have done that, I have it for the HList. Now let's go ahead and let's do it for the iterative case. Sorry, for the base case, and this is going to be a bit different. So the way that it works is that as I showed before, it grabs one method, and then it tries to split the definition, and then it finds a smaller piece of the HList until it reaches the end. But that's not the only way to do it. Like the last element doesn't have to be HNIL. It can be something else. So what we can do is we can define, let's say, let's call it HNIL QSB, or it could be base, whatever. And then here what we have is we have the same. So we need the K for the field name and H for the field type, and nothing else. We have reached the end of the HList. Now I'm going to define the parameters later, but here what I want to do is I want to provide a string bindable of the field type. So in this case it would be something like this. But this also needs to be an HList. So what I'll do is I'll just define that. So I could define one more step, but it wouldn't make sense, like because it would be one extra call that probably wouldn't do anything. In this case, I can stop short one method called earlier, but saying, hey, this is the last non-empty array in the case class. Obviously, this would fail for a case class that doesn't have any field, but yeah, who would want to do that in this case? So now what I need to do here is I need to have an implicit QSB. Let's say head QSB, and this is going to be a QueryStringBindable of H, and then I also need the witness because I need access to the field name, and then let's do a new derive QueryStringBindable. Let's see if we can make this prettier. So, okay, cool. Yeah. Now we are going to get access to the query string parent name. Here, what we're going to do, this is going to be super simple. So we're going to head QSB, unbind, and then we're going to use the query param name, and we're going to have the value and then the head, because we just want this part, we don't want this one. Now I don't need to concatenate with the ampersand. That will be done here, so it will iterate through the different methods in a recursive fashion, and then it will append them all together. Now if I do it for this, so what I need to do is I need to follow the same approach. So we need to bind that value. So let's use QueryString param name, and then let's also use the params. And then what we're going to do is here we are going to map. We need to flat map. The flat map is only required because, well, this method will call another method that returns a write, so we need to flatten them. But in this case, we don't need to. So let's do the error. So this is a left of error, and I think I should be doing this. I get which one failed. Okay, so once I have this, what I need to do is I need to have the right, and here we provide the same thing, so we need to construct the field, and let's just copy this, and here would be HNil, and this would be head. Yeah, so I think that should be it. Let me check. So let's create again. Let's just really quick. Let's create this. Let's import generic, or no, I don't want generic order this time. I want to have a derive, and that's it. So I don't need to import Shapeless, so that's not needed. And then what I can do is I can do employee QSP, and I can say derived QueryStringBindable of employee. Oh, I missed out. Nope, this one. Oh, come on. Did I it did compile, right? Okay, that's interesting. Console. Cannot find examples. Derive. Oh, right, yeah, because I imported everything. Yeah, that's the reason. Okay, cool. Now, once I have this, let's create an instance. Let's say Alice. And what we can do is with that employee QSB, we can unbind, and let's call it the key we won't use, and let's call Alice. So as you see here, this has converted Alice into its name. So we have Alice, number, and manager. And we should be able to do it the other way around. So just let me define it. So params, and this would be a map of name. This would be, oh, it's a sequence of Alice. Then we would have number. Yeah, it's a sequence because of repeated query parameters. So this will be 42. And finally, manager. And this would be a sequence of false. Yeah, so once, oh, yeah, right. This needs to be strings. Now, once I have that, I should be able to do employee QSB, bind the key, doesn't matter, we are not going to use it, and then we have the params. If I have that, then I can see that we have a right employee, and let's say that I mistyped something like numbers, and I try to bind it again, I get a none. So yeah, that's probably we could have done a better work at propagating the right value. Or actually, let's I think this is more like something like this. So let me clean that up. So I'm going to provide the wrong type. Here I could see I couldn't bind parameter number, cannot parse number as int from input string AA, and that's the error. So yeah, I think that's about it. If you're interested in the subject, I can't recommend the book enough. Probably I said a few things incorrectly, or quite a few things incorrectly, even if I could go ahead and implement the type class for this for them. But yeah, I hope that you like the introduction, and yeah, that's it. Thank you.